here we go. Um, so, I wanted to talk. I've been at the center of the development of IOTA 2.0 since, since there are people beginning to look into it, right? And as part of the people initially hired to to work on this problem, and eventually I started directing the department and hence the project, right? And so I wanted to share some insights. Now, of course, I could have done a talk about how it works and such, but in some ways, that's how we want it to work, right? Because there's a lot of different ways that you could build a protocol, right? There's a lot of different had a lot lower standards and just want to copy some other solution, right? And so, if we just go over the basics of what is the protocol and how does it work, then you really miss, you really kind of miss the why. You just see the trees but not the forest. So today, I really want to take a look at Coreside and the IOTA protocol and take a step back and try to understand our motivations and the problems we're trying to solve, what the solution that we developed is trying to achieve, right? So so first we have to talk about the problem, right? The problem we're trying to solve. Every single problem, every single solution should be solving a problem, right? And it should not be part of a vacuum. All right, so here's the fundamental problem, right? For digital actors to interact, they need a shared state, right? And if you control someone who can control that shared state, can control the applications and thus control the users involved, right? So this is true in numerous ways, right? If you want to say, like, you want to go to a website, even, all right, you type in the domain name, and then that your computer needs to resolve that to an IP address, and it's you do that through DNS, right? And so that DNS is a shared state, right? And that allows you then to interact with another digital actor, okay? And all interactions are like that, right? If a content producer produces some sort of video, you want to watch that video, somebody has to host that somewhere, right? You have to then have a shared state of the video being somewhere, right? And so the information is available for you to click on and such. If you want to transfer money, you have to have some sort of shared state about who has what money, right? And this is how applications this is how applications work, right? Yes. And so the idea, though, like the observation, though, is that if you have control of the shared state, right, then that gives you power, right? And that gives rise to what I call a global digital authority, right? And the reason why I stick the word global in there is because today more and more people are interacting, right? The state is getting bigger and bigger because we're in a global, ever digitizing, ever globalizing economy, right? That's where everything is going. All right, so like maybe like what's an example, right? I mean, going back to content producers, right? If you have a platform that hosts some sort of content, videos, or some sort of media or something like that, right? That is the shared state that is being shared then between all of the users, all the people who want to consume the content, and also all the content producers, right? And that you can record like permissions and do it, pay people based on that and such. Now, if that platform is controlled by someone, then they have control over the whole system, right? They can censor content, they can charge money, right? They can extract a profit. All right? And they become an authority, right? They have control over something. Okay? And so and also the more interoperable that you want things to be, right, then the more power that this gatekeeper is going to have, right? I mean, just sort of think about, let's just think about video streaming services, right? If you have all what is the most convenient thing for you, right? The most convenient thing would be for you to have all of the movies on a single platform, right? So you just can go to one platform and then you can get any movie you want to watch it, right? That is the best. Okay. But what is the problem? A monopoly, right? This is a centralized solution. This is a monopoly, right? They have now control. They can charge you whatever they want, right? They can charge the content producers whatever they want, and this is bad. So you have what's convenient for you, right? On one sense, but then this is kind of also bad for everybody, and that's exactly what's happening with video content now. Is that, well, every video content producer is like, well, why should I give Netflix a share of the profits? I'll start my own streaming service. And then you have this fragmented space, right? Is now non-interoperable because every single content producer is having their own streaming platform, and now digital actors are not interacting together because they can't agree on a digital authority that's not going to that's not going to be monopolistic, right? And so this is the idea, is that ideally you don't want anyone to control the shared state, right? Or you need the governance of the shared state to be such that that is not a monopolistic force that's extracting value, right? So one example maybe is sort of DNS, right? Is like a fairly, like, this is a centralized service, but you cannot, as DNS is value extraction, right? But other things it could be. Okay. So this is where DLTs come into the picture. Is that a DLT is exactly something that can maintain a shared state, right, between parties that are don't trust each other, right, or don't want to. But the problem is that most DLTs are, maybe they're not centralized, but they're heavily centralized. They're basically these oligopolies. Maybe not monopoly, but you have a few miners or one organization that can control a whole chain, and that's that, right? And so you're not that group of people. Like, the DLTs right now are controlled by certain entities, and so if we try to use them as sort of like a global digital authority and maintain a global digital state, well, the people who right now, there you can see ways that these entities are extracting value, and they will extract value out of all those applications. All right. So this is where we get to the idea of digital autonomy, right? And this is something that in the future, I'm hoping that you'll see some blog posts on, or, well, I'm writing some blog posts about this, writing some documents I want to share with the world, because I think it's a powerful idea. What is digital autonomy? Digital autonomy is control over your life, right? Over your digital life, right? It allows you to live your digital life, and your digital self has protections, right? Your assets are protected from value extraction. Your data is protected. You have some privacy. You have your identity is not subject to some controlled by some for-profit entity, right? That you have fair treatment and equal protection. And when I say that, what do I mean by protection? Many things: censorship, political censorship, or economic censorship, or value extraction. Value extraction is huge, right? How can we have build a digital economy on an infrastructure if there are leeches leeching out money from this, right? We, as the users, at the end have to foot that bill, and it's not going to be, it's not nice, right? Of course, it has to be easy to use and accessible. So digital autonomy is the idea of you having a digital space and a digital life that is sort of yours, that you can control, right? And so we have this balance between we have a balance between digital actors, this global digital state, right? And digital actors interacting together. But to submit and work in that, you have to, you also have to work into that and be free, right? And you don't want to give up all of yourself. You want to balance the needs of society, right? And the ability to work together with your own personal freedoms, just we have in our physical world, right? Right. So yeah. Now, so digital autonomy is similar to decentralization, but decentralization is just not enough, or it's not specific enough. Like decentralization is requisite for digital autonomy, right? I mean, because if you have a centralized entity controlling everything, okay, well then they will control everything, right? That's not good enough. But what is, you know, so we need something more though than, just having three validators on a chain. That's not good enough, right? And so digital autonomy is to actually describe and getting into more of the details of what we actually need out of decentralization. All right, so the mission of the IOTA, the foundation, right? What we're trying to do is basically what we're trying to do in so many words, right? Um, so yeah, so this is this is going to be a long road, right, to actually build it, because we need a global infrastructure, a global digital infrastructure. This is huge, right? And it's not going to be built overnight. IOTA 2.0 is I guess it's the second step, right? Current mainnet is the first step, but this is the next steps on this continued mission, right? Now, to understand how we take this first step, the rest of the talk, I want to focus on the design principles, the things that we have that actually allow us to, enable to this to happen, right? What do you need from a DLT in order to do this, right? And I think we're all fairly DLT friendly people, so we can I don't have to sell it to you that this digital infrastructure should be some sort of DLT, right? But assuming it's a DLT, what does a DLT need to do? Okay. All right. The first design principle of IOTA 2.0 is accessibility. Now, before I can talk about accessibility, right, I want to contrast it with the current state of blockchains, right? So in blockchains, right, what we do is we have a mempool, right, where people submit their transactions, the .cr transactions, and then we have a bunch of block producers, right? And there's not that many of them. And the block producers, miners or validators, it's different protocols. They select transactions and they produce blocks in there, right? And they decide who gets in there based on a fee-based auction. And also, let's be honest, MEV, right? they can order these things to extract the most value, right? All right, so that's how it works, right? But the block producers as an oligopoly. It's not a monopoly because there's more than one block producer, but it's not that many of them, right? And you have to go through this. If you want to use a DLT, right, if you want to use a blockchain, particular blockchain, you have to pay a miner to give them your transaction. You have to go through this system. There's no other way around it, right? You are forced to deal with this group of actors, okay? Now, why is it an oligopoly? Why do I say that? Because, an oligopoly comes from the word oligarchy, right? And so it's because you have a few participants. So when I say participants, I mean block producers. You only have a few block producers. Here's why. So consider the block creation rate. Now, the block creation, the number of blocks it can produce at any time, right, is the block creation rate times that time, right, which is the number of block producers you can have in that time period. Okay. Now, here's the problem. Lambda, the block creation rate must be small. Why? I have because the large block creation rate means lower security, and in practice, this means that you cannot have any more than one block per second, right? Typically speaking. Don't get me started on Solana. They kind of fake their numbers, and what they call block is not really block, but yeah. And so here's why. I need to get to the picture now so you can see why. I mean, if too many blocks are being created at once, right? So it's not very, you have delays and such. As if you have too many blocks being created, then you have multiple blocks being created at the same time. And if you have blocks being created at the same time, then you have forks, right? And okay, blockchains, they can deal with some forking, right? But if you get too many, every time you have a fork, the security begins to degrade, right? Because you split you kind of split the validators of working on one or the other. And so if you get too many forks, the security just goes to zero. So as the block creation goes to infinity, security goes to zero, right? And in practice, typically, where the happy thing is no faster than 1 per second. Okay, so it's the chain part of the blocks. Now what this does, right? So because we have this oligopoly, we have these two classes of users that are at war, or these two classes of actors, not users. We have the users and the block users, and they have opposite needs. Users use the network and create transactions, and they're the good guys, and they want cheap throughput, right? And they are actually creating value for the network. They're the people who are doing stuff, right? The block producers are just service providers. They bundle transactions into blocks. That's their service. And they want expensive throughput. Why? Because they want to extract as much value as they can from the network. So users bring value and block producers take the value, right? And this is the way of things, right? So this will not protect digital autonomy. It cannot protect digital autonomy because the block producers are a class of actors that are at war, that are a threat to the autonomy of the users. So, accessibility. Going back to the design principle, what we mean by accessibility is this. Users must be the same as block producers, because this is the only way to guarantee that their incentives are going to align, right? Mint your own blocks. You can also call this feeless, right? Because if someone else is minting blocks for you, then you have to pay them to do that, right? But if you can mint your own blocks, then you can mint blocks in a way without having to pay a fee. This does not mean, of course, free, right? Because it is scarce throughput, and something that is scarce will always potentially cost money at certain points of time, right? But that's something different. So feeless is not necessarily free, but yeah. But you don't have to pay someone a fee, right? Because you can produce your own blocks. All right. So how do we achieve accessible writing in IOTA 2.0? We increase the block creation rate with Dags. Haha, Dags to the rescue, right? Actually, the answer to how we achieve everything basically in most of these principles is Dags. So, you saw this calculation before. The max block producers is the time, is dependent on the block creation rate. In IOTA, the block creation rate is only bounded by the computational power and the network resources, right? The nodes, right? Of course, nodes, can't process infinite number of blocks or transactions. They can only process a finite number. And so this bounds the throughput, right? This bounds the creation rate, and this will bound the number of block producers. And in IOTA 2.0 is, depending on how you count, since the blocks don't need to be all the same size, depending on how you count, somewhere in 100 to 1,000, right? Which is much better than 1, right? And here's why, right? Here's how the Dags saves us is that, well, if two things at the same time, then the next block can just reference both of them, and you have a DAG. It's no longer a chain. Ooh, yay. Okay, DAG save us, that we don't have this linear structure. All right. Now, so now this gets better, right? So in blockchains, right, the number of writers or number of block producers is basically constant, right? It's determined by the network delay. The network delay is not going to increase with better technology, right? It's going to be about the same for forever, right? But as years go on, network resources go up, right? We have more bandwidth than we did 10 years ago. We have higher processing power than we did 10 years ago. These things will get faster, right? So in some number of years, Lambda will nodes will be 10 times more powerful, and this 100 to 1,000 range will go from 1,000 to 10,000, right? But blockchains will be stuck at 1, right? They can't go any faster than that. And so DAGs will scale with the technology, right? So this is hugely important, right? So Dags maximize the amount of accessible writing that you're going to be able to have. It maximizes the number of block producers you can have, right? Now, I will say that even with IOTA 2.0, at some point if today the entire world started trying to put all financial traffic on the Tangle, well, that's not everyone's going to be able to produce their own blocks, right? But it does the best it can for what we have, and it's going to be enough to satisfy sort of the DLT needs, right? And then we can work on charting solutions and things to increase the throughput, right? This is the first step of a longer thing. All right. And then I want to go back to the model, right? I had the first slide, right, about the mempool. Like the whole mempool structure stays, it changes, right? Users and block producers are the same, all right? You have a lot of them, and each one has its own mempool that can manage in whatever way it wants, right? And its mempool can consist of its own transactions, right? And then they create blocks, and each block has one transaction. All right, that's the IOTA 2.0 way of doing things. All right. And kind of talking too slow, I'll go through this fast. But another thing that's important is that we're enabling in IOTA 2.0 is the idea of being able to allow block producers to produce sporadically, right? So there's you always have to limit block production rate of every block producer with respect to some cryptographically verifiable symbol protection resource, right? Proof of work, proof of stake, or mana in our case, right? Whatever, you have to have something like that. Now, typically in blocks, and sorry, in blockchains, right? The model is based on sort of constant block production, where you have a service provider and they're making blocks at a constant stream, right? And so the average throughput is that like the amount of proof of work or stake or whatever you have dictates your average throughput over a very small window. But we can take that average throughput defined over a much longer window, right? Through this idea of enabling sporadic block production, right? Where okay, you want to send 3 transactions one day, right? And you do that. But those are the only 3 transactions you send in a month. Well, you're sending 3 transactions per month, right? You have very low throughput, so you don't need very much the resource to issue 3 transactions per month. It's almost nothing. But what's important is to enable the protocol so that you can send those 3 in a burst, right? Now, you of course have to mitigate have to have mechanisms, and this gets a little complicated in the whole mechanics of congestion control when everyone wants to send their 3 blocks at once, right? And you have to make some trade-offs and such. But that's resource allocation. But we do the best that we hit the best possible solutions with it. All right. So sporadic block production. That's what's required for accessible writing. All right. Okay. Well, halfway through, only done with first principle. So principle 2, parallelism. So again, I have to talk about something first. So there's 2 concepts: parallel processing and stream processing, right? Parallel processing increases speed. Stream processing increases efficiency. When a parallel processor, you have multiple cores inside your computer who are working independently. It's basically like several computers working at once. So you have a team, and this makes things faster to a certain degree, right? For many tasks, if you have 10 people do the task, it's faster than if you have 2 people do the task or 1 person do the task. Well, it's certainly usually faster if you have 1 person do the task. But you have to have the task be able to be doable by 10 people, right? Not all tasks are parallelizable, which is the idea of parallelism as a design principle. Stream processing is the sort of rate, right, that you're getting. Now, when you're stream processing, you're sort of processing things at a constant average rate. This is opposed to batch processing, where you get a big batch, you process it all, and then you wait for the next batch. And then you get the next batch, and you work, and then you wait, right? And so so here, what happens, batch processing is inefficient. be able to reach the rate that's required, right? In order for your machine to, so the higher the graph is, the more powerful machine you have, because it has to process at a higher rate. But in batch, you have to have a powerful machine, work really hard, not work, really hard, not work. Stream processing, you have a moderately powerful machine that just does the average, right? So parallel processing is better, stream processing is better. Now, there are many fundamental blockchain trade-offs, and one of them is parallel. You can do parallel and batched, or sequential and stream. You cannot have I spelled parallel wrong. Oh, that's embarrassing. All right. But you cannot have parallel processing and stream processing together, right? You cannot do it. Why? Well, because the block size times the block rate is is proportional to computational resources, basically, of the node, right? And which is fixed. So if you increase one, then the other one decreases. And transactions within a block can be processed in parallel. That's true. But blocks must be processed sequentially. You cannot parallelize the validation of multiple blocks if they are in a chain, because they depend upon each other. And each block represents batch. So you have two options. The first option, if you have small blocks that are faster, then you can stream process, because you have rapidly receiving blocks, but they're all itty bitty tiny. There's nothing to parallelize inside them. Okay? Or, on the other hand, you get these big blocks, and you get a big block, and you can parallelize all of the processing within that block, but each big block is a big batch. Can't have both. And also, keep in mind the previous conversation of that the block creation rate has to be small in general. So add that also into this mix. Okay. So IOTA 2.0 has both parallel and stream processing, because we have a DAG, right? Remember, we have the high block production rate. All blocks are processed on arrival. And so blocks that are, that are concurrent, that are not ordered in the DAG, can be processed in parallel, right? And this and yeah. So you have blocks that not all the blocks are ordered, so you can parallelize things, and you're getting them at a high, very fast rate, and much higher rate than you can even possibly have in blockchains, right? All right, so what this does is it produces the largest possible throughput that you can get on consumer grade hardware, which goes back to the original principle, right? Is that the hardware requirements basically dictate the number of writers, right? So this actually feeds back into the first principle, because by being as efficient as possible, people have their machine, their resources, and then you can try to make it at as many blocks as possible, and then you can have as many writers as many block producers as possible. And I would argue that this is our primary architecturally unique feature. It was also the thing that hardest to do, right? To try to make this happen. We spend this takes a lot of thinking about how to enable this. A lot of ins and outs. So a lot of the things that we have in our solution, right, are because of that principle. All right. Next, volume and velocity. All right. So what are the requirements? Well, there are only two. The first one is lots of throughput, global, big, lots of throughput, right? Second one is it has to be fast, right? You can't be, sitting there in the, passport line trying to wait for your passport to beep, and you scan it. No. You want to beep. So this, this has to do with confirmation time, right? That's part of it, but it's actually something more, right? The whole process has to be slick. You can't have it go down. You can't have things be slow, right? Quick. That's what you need for a global infrastructure, right? Now, so this is kind of not very precisely put, but this is what we try to capture with the words volume and velocity, right? Now, caveat, IOTA 2.0 is not yet fit for a truly global infrastructure, right? You can't put you can't replace Visa, or you need millions and billions of TPS to do that, of course, right? But it's still a design principle, because it's a first step in that direction. I want to explain how, right? So high throughput, IOTA 2.0. Ultimately has to wait till sharding, right, for us to get to really, global throughput, right? So that's that's why I'll still have a job after we get IOTA 2.0 out, right? Um, Efficient processing, right? So as I was talking about before, for the same amount of hardware, it's really important that we can try to put as many transactions as possible. And this actually makes a sharding solution easier, right? A potential sharding solution, because you have to get to it less, right? Like yeah, like the bar, which, okay, we need to shard now, is higher if you're being more efficient, right? Um, yeah. And also, we would argue that our DAG structure makes IOTA 2.0 prime for layer 1 sharding, right? I mean, any sharding actually looks like a DAG, right? I mean, even in blockchains, right? When you start having blockchains and then you have blocks referencing other blocks, you've got a DAG on your hands, right? So any sharding solution in blockchains is a DAG, right? So let's just start with the DAG-based architecture to begin with. Yeah. High velocity. Now, we have quick confirmation times. A lot of chains have quick confirmation times. We have competitive confirmation times, but also there's less things that need to be done, right? We're, especially since we've cut out, like, we've removed the block producer class, right? When we process things on arrival, we cut out a lot of steps, right? Before, you take a transaction, you put it into a mempool, it sits in the mempool, gets sequenced in the block is issued to the network, the block is validated, and then the transaction is executed, and then the block receives approvers, and there's all these steps, right? But in IOTA, it's a lot faster. You are your own block producer, so you create the transaction, immediately put it into a block, ship it out. All the nodes receive it, and the transaction is executed on arrival, right? And that's the magic of the parallel reality-based ledger state, right? And the block starts receiving approvers and gaining an approval weight, and that's how on-tangle voting works, right? It's a very lickety split. So this process is sort of simpler, even in the architecture, by removing certain things, right? And this will help gain speed. There's another thing about velocity that's important, right? It's this property of dynamic availability, liveness. I mean, if we have a global infrastructure, you don't want to halt ever, right? Like, you want to be sitting there at the airport, right? And you want to scan your passport, and global infrastructure is down, can't get on your plane. You can't have that. It has to continue working always, right? It has to be incredibly robust against crashing. And this is one of the properties of Nakamoto consensus, right? This dynamic availability is not unique to IOTA, but it's not ubiquitous amongst all blockchains, right? Every single blockchain can choose between, favoring liveness or safety, right? And Tendermint and Cosmos type protocols, they choose safety over liveness, right? But Nakamoto consensus, one of the things that was so remarkable about is how live it was. If all the miners in the world crash except for one, the Bitcoin will still continue, right? That is a remarkable property. That is a great property, right? the block production rate will also slow down, but eventually it'll go back up. But you can resolve any partition, right? There's transatlantic cables cut. All the continents, in the world, they do their own. They have their own forks. The system's live, but then the fault, the partition is resolved, and that's that, right? Classical consensus is only 1/3 crash fault tolerant, and this is the problem with Tendermint, based systems, right? Like, if you have 1/3 of the validators crash, it stops, and to me, that's unacceptable. is an architectural, and this is, we could debate about this, whether or not this is, because not everyone would agree with me, but I posit that to be a robust global infrastructure, that this is unacceptable and you need dynamic availability. So what we have in our protocol, right, is we have developed a mana-based, Nakamoto consensus on a DAG, right? We call it Nakamoto consensus on a DAG, right? And we're not using proof of work and such, but it has this the same property of that the Tangle will always continue growing, and there will still be confirmation. And because we're going to favor liveness over safety, but as other protocols do, we have a multi-tiered consensus that enables sort of a safe finality too, right? And Ethereum has this, and Cardano has this. No, this is not unique to us, but where you have two senses of sort of finality, where you have like confirmation and finality, where confirmation will always keep on happening and is very live, but then you have finality, which won't be reverted but can halt, right? And this allows clients, users can decide which one they want to use for whatever application. If you're paying a coffee, you can go with confirmation. If you're buying a house, you should probably wait for finality, right? And you can also measure the difference between the two flags, and see and you can use that actually as a tool for determining if there is a problem, right? So essentially, is a very this multi-tier consensus based on dynamic availability. And, we are not the pioneers of this, but we sure as heck recognize that this is an important property, and IOTA 2.0 will have this, and we need this so that we can be a global infrastructure that is fast. All right. So now, social dynamics, right? This is the last principle. It's good because I'm running out of time. This is a little bit harder to explain, a little harder to grasp. I think it's a little less technical. So only one of these that doesn't have to do with a DAG, actually. But yeah. So the individual versus the digital world. What is your digital self? And this is actually an interesting question, right? Like, think about your digital life. It's based on basically the contours and the ergonomics of the various applications that you use, right? I mean, you're watching this presentation on a computer, right? And you're using some web browser that you like or dislike, and that's what you're doing, right? And how your relationship, you have a relationship with your web browser, you have a relationship with all of your applications, right? And this is your digital self. The settings that you have, the bookmarks you have saved, the friends you have on social media, like the contacts in your email, your favorites in Spotify. These things comprise your digital self, right? You have a sort of, as not a digital identity in the strict like self-sovereign identity sense, but in a more digital twin, like where you have, there's a part of you that sort of exists in the digital realm, right? Now, if we want an infrastructure that is going to protect digital autonomy, then we have to understand what digital autonomy is. It is about that digital self. It's about that digital space. It is about how you are using the various applications that you are using in front of you on a day-to-day basis, right? And this is kind of hard because, when you're designing a protocol, the protocol is far away from the person, right? And I think ideally, personally, I think in a real good digital infrastructure, like, you should sort of be able to sort of forget about the underlying mechanics of everything that you're working on, right? You shouldn't be like, oh yes, I'm making blocks and transactions and adding them to a DAG every time you're surfing the internet. You don't want to think about this stuff. You want this to be extractified away from you, but you can't have that extractify too far, because you need to see yourself in the protocol. The protocol has to have a sort of a copy of you, or a recording of yourself, right? A mirror, if you will. Like, think about your kitchen. Another way of thinking about this is, you all have some sort of kitchen, right? Whether or not you're sleeping, live on your friend's couch, your parents' house, you rent, or you own your own home, right? You've got a kitchen, and there's pots and pans. You all have your favorite pan, right? and you know where that is, right? You have that favorite coffee mug, and you also have that annoying coffee mug you use when your favorite coffee mug is dirty, right? And you know where these things are. And this is your space. This is your, and even though you don't own any of it, but it's still sort of yours, right? And so what we need is to sort of imagine if you were to sort of take a copy of that and record all of this and put it somewhere, and so that you can access your kitchen anywhere, right? And so that your kitchen somehow is protected, so that you know even if you don't own your house, like if you're renting, if you got rid of your house and moved to a new place, that you could take your kitchen with you because you had it all recorded on a digital ledger, and you arrive to your new apartment and you do click, and then your kitchen, your old kitchen with all of your favorite coffee mug in that exact spot appears, right? That's what we sort of, when I'm talking about the individual self and social integration, right? About how the relationships that we have as people with each other, that gets transferred on to the ledger, right? And so you have a spot, right? You have some bytes somewhere that represent yourself, that you can customize and that can be protected. How do we do that in IOTA 2.0? Accounts. That's how. We have so what we're going to do is we're going to, alias outputs are going to become basically accounts, right? That's kind of what we were thinking of originally, and that's why we use the word alias, but account sort of fits better, right? And this means that you'll have a static identifier, right? Then that's what you're going to access the DLT with, right? If you send funds to someone, you would send funds to an account ID, not necessarily to a public key, right? Because you want to abstractify that stuff away. You don't want to be like, so what's the private key, public key of your wallet that you're that you're generating for this transaction? Well, I mean, ideally, what eventually we would like to have this be, these not have just a static identifier, but have human readable names like email, right? And so you can send money to an email, but we're not there yet. Future versions of IOTA, right? But this is the first step in the direction of having accounts, and to give you a static thing. And then what's important about this is that then you can manage, through this you can manage your mana, your tokens, your digital identity. If you have a digital identity that's resolving through IOTA, you connect that to your account, right? And it makes it so how you interact with IOTA, right, is going to be through a wallet, right? And so I imagine many of you guys have Firefly wallet, right? But you don't want to be necessarily tied to that, right? What if the Firefly team adds some stupid features that you don't like? What you want is then, okay, you can just go to a new wallet, open it up, and all import your entire digital self into there, moving your whole kitchen into a new place. You can't do that with email. You can't do that with social media, right? You have all of your contacts on contacts listed in your Gmail account. You switch to Yahoo email, then you can't take that stuff with you, right? If you start sort of a new account or want to change something about your profile on Facebook, you kind of have to start over, right? And you kind of have to torch your old place and build a new one. No. And this is this is a way to keep applications. This goes actually back to the beginning I was talking about, is that this idea of account abstraction is really a way of you not becoming dependent on certain service providers and people who and prevents you, gives you freedom, and your value will not be extracted by people, right? Anyways, I think I'm now starting to ramble. So yeah, that's that. Thank you for listening to me. Yes. So yeah, I was not looking at any of the chat, so maybe there's some questions there. Probably should time for questions.
We still got time for questions, but I first wanted to thank you very much for your presentation. I was on edge. I really liked how passionate you were about it, and yeah, you carried it over in such a fun and exciting way to listen to, even though it's such a, how to say, maybe dry topic. It could have been a dry topic, but you presented it in a fun way, of course. Yeah, really liked it, appreciate it very much.
You.
And yeah, we got a couple of questions for you. You don't need to check the chat. We've got everything sorted out for you and pre-filtered. And yeah, should we start? Are you ready for the Q&A session, Billy?
Sure.
All right. The first question is, why is Lambda equal to 1 second block time in blockchains an issue if you can just scale up blockchains?
Well, because it's a factor. Okay, why is it 1 second? I mean, that's more of an observation rather than like a rule, right? But it is, if you increase it's because of the delay, right? The delay, if you have people produce blocks more often than 1 second, then, because it's on average 1 second, it's not like every second everyone someone takes turn produces block. People are randomly producing blocks on average about once a second, right? And if you increase that too fast, then you get multiple blocks. That's fork, right? And it is a function of the network delay, which is not going to decrease really. Like, maybe it will somewhat, but it's not going to decrease like by a factor of 10 or factor of 100. So this is going to stay there. And so that's why, and so every single chain, it has done some sort of calculation about, taking their security model and their, consensus algorithm and saying, well, how fast can we increase this and, not sacrifice security? And it's typically 1 second or less, like Bitcoin, is once every 10 minutes, right? So a wide variety of answers, but, that's where you start seeing the limit. You just don't see any that are faster than that.
Exactly. Funny that you mentioned Bitcoin. It was exactly the thing that I wanted to talk about as well, because like you were stating, it's for security purposes, and Bitcoin is through the algorithm trying to get the how do you call it, the mining difficulty out of that, right? So the algorithm was catered towards not making it faster, but trying to get it every time on these 10 minutes, right? So
yes.
It got progressively harder, the mining challenges.
Yes, well, that's the dynamic resource allocation, right? That's the thing that you need in any sort of effective resource allocation, because you always have to regulate access with respect to some sort of cryptographically verifiable resource, right? And so you always have to have the block production rate basically sort of adjust so that when there's more demand, that takes more resource to issue blocks, and if there's less demand, then it takes less resource to issue blocks. All DLTs need this, right?
Definitely. It's one of the core principles for distributed ledger technology. All right, I think that was the first question. Then the second one is, I think you even answered it in your presentation later down the road. Will we see batching of transactions, in parentheses, multiple transactions in a block in IOTA in the near future?
Not in the near future, because there's not a reason really. I mean, like, yeah, it's not going to be an IOTA 2.0, right? Maybe in future versions, if someone presents a cogent reason to have it, because if you need to issue 2 transactions, then you just issue 2 blocks, right? And so,
all right, that was a quick and precise answer. No, very nice. Thanks for that one. Then the third question. A lot of IOTA's utility will come from people building applications on top of layer 2 chains. With that, however, IOTA will inherit a lot of problems we see with classic blockchains like Ethereum. Can you please give a few thoughts on why you have to make this trade-off and why you can't have smart contract functionality at the Tangle level? Thanks in advance. I think Dom even touched on that point a little bit at the beginning. But
yeah, well, yeah. But smart contracts on layer 1 is tricky because of Dags, right? Because you don't have a total order. And so, like, a lot of smart contracts platforms just basically, like, okay, if we want to just copy what Ethereum does and their smart contract platform, doing that on layer 1 is tricky. Why? Because, like, well, you would need to totally order everything. You would have to strip out everything of the DAG and have a chain, right? Because you would have to do, Ethereum does 1 transaction at a time, right? And it's because how every transaction mutates the ledger is dependent on all the things before it, right? Like if you have, say, register a name, right? And you try to register a name and I try to register a name, right? One of those things, if we try to register the same name at the same time on Ethereum, one of those things is going to fail, right? And what's going to fail is the one that comes second, all right? And so you can't just for free put that into UTXO, right? And so you need a smart contract platform that works for UTXO. And so there's work on this and that you can see happening in this space, and this is a very interesting topic. But doing smart contracts on layer 2 is, with the ISC chains, it's quick and easy, delivering people something that's useful faster, right?
Yeah, exactly. I mean, I think I asked Dominic a similar question, and he was talking about this assembly ecosystem part that your guys are developing still in the background. It's a future part of the roadmap. And it's basically that, right? So getting smart contracts on the main chain and having the finality on there. But thank you very much for this one. Then comes the fourth and last community question. After that, maybe I will still drop one or two in. But it goes as following. Regarding parallel processing versus batch processing, does IOTA 2.0 not have batch processing as well, with each validator vote resulting in a batch/set of no accepted transactions to be processed?
No, because yes, because we process all the transactions upon arrival, right? Which is very exciting, right? Because this is how we have the parallel reality ledger state, right? If you issue a transaction, okay, let's say that we have two transactions, right, and they're a double spend, okay. In the non-double spend case, it's super easy, right? You get something, you get the block, you look at it, all right, you immediately apply the change, all right, and you go, right? Okay, what do you do? There's no need to wait, right? What do you do when there's a double spend, right? Well, what you do is you apply both of them, but you create a different sort of what we call reality or a fork forms. You can call it branches, realities, forks, right? And we remember both, right? And then if you issue something building on your spend and I issue something on my spend, right? I can, we can do that, right? And then you can track that. You can track, okay, these transactions depend on this side and these transactions on this side, right? And then we'll just keep both until one of them gets decided, until the conflict's decided, and then we stop, everything that dependent upon the loser, none of that's going to get finalized. Everything dependent on the winner, that gets finalized. But it's just a matter of the batch that we have to do is just walking through the pass cone and switching flags from yes to from to accepted, right? We're not doing any validation rules or applying any logic or anything like that, because we've already done that. So yeah, so the heavy part of the transaction validation and storage, all these types of things are just done immediately upon arrival.
All right, thank you for the answer. I hope it answers your questions. Now that I'm looking on the time, I think there's only time for one more little question from my side, and then we would go over to the next speaker. And that would be, I think, a question about you yourself as a person. How did you actually become a part of the IOTA Foundation since you got the background?
Well, that's
just a brief little because I was interested and wanted to
well,
know.
That's a less inspiring and interesting answer. I finished with my postdoc. I needed a job, and I went to a picnic with an IOTA employee and went, "Oh, I know someone who will hire a theoretical mathematician." So, yeah, that's how I got into DLT, and I didn't really know anything about the space before that. So my baptism by fire, like my introduction to DLTs was baptism by fire of so we have this coordinator. we want to get rid of it. Figure out how. Learn what it is first, So, but that's actually sort of, but it's a sort of a great way, I think, of approaching these problems, right? And to be completely honest, there's a lot of people in the foundation, well, in the research department in particular, that came at it from this perspective. But one thing that this did was it actually brought a lot of different backgrounds and perspectives to the problem, right? For me personally, since I, I didn't have really any preconceived notions and such, and so I kind of was able to form my own opinions about how things can do. And I think this was very important for all of us, right? To be able to do, right? And so yeah, so since we attracted people, research and development, our researchers and engineers that we hired came from a lot of different areas. We had a lot of tools at our disposal, and a lot of very interesting conversations allowed us to develop a very, very good solution.
Right, thanks for the insights, and I think this was a perfect 3-point landing, perfectly on time. And yeah, thanks again for your presentation, Billy. And I hope we will see us next year as well.
No, thank you very much. Thank you for organizing this.
Of course, you're welcome. Thanks. Bye.